Example 3.3, looking at graduate school admissions. We're going to learn a new technique here, and it's called a probability table or a contingency table. They mean the same thing. But let's first of all look at the problem. Suppose you've applied to two graduate schools and believe that you have a 0.6 probability of being accepted at school E, 0.7 probability of being accepted at school F, and a 0.5 probability of being accepted by both. It asks us to first organize this information into a probability, or in other words, a contingency table. Now, if you haven't seen these before, we're going to take it slow and make sure we're going to be doing a lot of these this quarter. We're going to start with a basic box, cut it into 4. We know you can either get into school E or not get into school E. And hopefully that makes sense. You either get into a school or you don't. There's going to be no waitlisting here. It's either in or you're not. You could be accepted at school F or not at F. Notice I extended those out a little bit. The probability, the total probability to be a valid probability distribution must total 1. So that's going to be in that bottom corner there. Now we have some information that we're given. We're given that the probability of getting into school E is 0.6. The probability of getting into F is 0.7. And the probability of E and getting into E and F, F, is 0.5. We're going to use this information to fill out the table. So let's start with what's given. The probability that we get into school E is 0.6. So we don't care what happens with school F. The probability of getting into E is 0.6. Same with probability for school F. We don't care what's happening with E, but we know the probability is 0.7. We also know the probability getting into school E and school F is 0.5. Now the table obviously isn't done yet, so I'm going to change colors so that we can see, hopefully you can see clearly where these numbers are coming from. So I have to calculate the rest of the numbers in this table. We know that we have to add across to be 1. So if we get into school F, the probability that we don't get into school F is 0.3. And likewise, for getting into E or not getting into E, that has to be 0.4. We're effectively using the complement rule again and again and again. Once again, we have an unknown here. It has to be 0.2. And then we can fill across, and we can take a moment to check ourselves. So if we add down in each of the columns, we get the right number. If we add across, we get the right number. If we add down and across, we end up with 1. So this looks like a valid probability distribution. Now the next one's number 2 says use 3 different methods to determine the probability of being accepted by at least one of the 2 schools. And we're going to label each of the methods. So we want the probability that we get into at least 1. And I'm only going to label that the first time. And then from there on, we're just going to come up with the probabilities. Thinking about it, if I use a different method, should I come up with a different probability? And the answer is no. All right, the probabilities won't change. But let's start first using the table, just because we have that right in front of us. We know the probability of getting into, let's see, we want to know the probability of getting into at least one school. Well, we know the probability that we get into both of them is 0.5. The probability to get E and not F is 0.1, plus the probability of F and not E is 0.2. And there we go, 0.8. And that should make sense that we see that we get into neither is 0.2. If we add that together, you would get the 1, total of 1. And you'd be like, well, that sounds really familiar. That sounds like that complement rule. And it is. Remember, we can take the probability of at least 1 is going to be 1 minus the probability that we get into none. 1 minus, and then I'm going to look at the table and use that 0.2, and I get 0.8. The same number. Perfect. The last one is there's overlapping, or at least I'm guessing there's overlapping, and we're going to use that general addition rule. So the probability of E or F is that probability that we get into E plus the probability that we get into F minus any overlap, because we only want to count it once. Let's see, the probability that we get into E is 0.6, and the probability that we get into F is 0.7. Let's say you just stopped right there. What did these two total? Well, it totals 1.3. That's more than one, so you know you've got a problem. All right, you know there's a problem. We need to do something else. And we need to take away that overlap, which is the 0.5. And we once again get 0.8. Use the one you like. I honestly, this is what I use most of the time. But do know the rules, have the rules available, especially for quizzes and exams. But as I'm doing the calculations myself, I tend to use the probability table. The next question is determine the probability of being rejected by both students. So the probability of not E, so you didn't get into E and you didn't get into F. I'm going to use the table and just, I know it's 0.2 from the table. I can read not E and not F is right there. How about the probability of being accepted by one, but not both schools? I'm going to use, once again, the table. I want to know what the probability of getting into E and not F. So I'm only getting into one school here, and the probability of F, but not E. Well, E and not F. Let's see, so I get into E, but not F is 0.1. With the same logic, the probability to get into F, but not E is 0.2. And just to be clear, it is this 0.2 here because we got into F, but not E. Remember, we're trying to get into just one school. And we get 0.3. And I use the table for that. Now, instead of using a probability table, we can also use a Venn diagram. I'll be honest with you, I want you to be familiar with Venn diagrams, but as a general rule, I will use a probability table. Can I grade Venn diagrams? Yes. Do I find them useful at times? Sure. But I really like using the contingency tables. I'm a mathematics undergrad, and those just work better for me. So let's say we have a piece of paper here, and the probability that something happens on this in an event is 1. Okay, so our probabilities are 1. We know that you're going to get into E, and the probability of that is 0.6. So the probability of getting into E, oops, sorry, this shouldn't be an equal, it should just be 0.6. And we know they overlap because we're told the probability of getting into both of them is 0.5, and the probability of getting into F is 0.7. Now, these are not to scale, so don't be confused. You're like, well, they're not to scale. Yeah, that's fine. Don't worry about it. I'm just trying to represent what's going on here. I'm going to change the color to red. So I know that this is 0.5 here, and I'll need to know what's out here to add to 0.5 to get to 0.6. Well, that has to be 0.1. Because if I add 0.1 and 0.5, it gets 0.6. And the same rationale here gets me to the 0.7. What's the probability that I get into neither school? Well, I know inside the circles, I've got 0.1 plus 0.5 plus 0.2, and that ends up being 0.8. So what's left over is 0.2, and that's getting into neither. Remember, to be valid, everything inside here would have to total 1.0. Now, for number 6 below, suppose you only know two things. You only know that the probability of getting into E is 0.6 and the probability of getting into F is 0.7. But you don't have the probability of getting into E and F. You have no other additional information. So we want to know what is the largest and smallest values for the probability of E and F. So what I would suggest doing, and this is one time I would suggest a Venn diagram, is I would redraw it and think, okay, I know that I have the probability of getting into either one, or excuse me, the probability of everything has to be 1. I have 0.6 for this one and 0.7 for the other one. They have to overlap because if they don't, if I add these two together, I end up with 1.3. So how far am I over for this being valid? Well, we know the probability of E is 0.6 and the probability of F is 0.7, so that totals 1.3. Not valid. Well, if I subtract 1, which would make it valid, I know that they have to overlap by 0.3. This is the smallest that probability of E and F can be. They have to meet, this is where they meet the least, this is the smallest overlap. For it then to still be valid, because this would be 0.3, because 0.3 plus 0.3 is 0.6. 0.3 plus 0.4 is 0.7, and if I add these together, I get 1. So the probability into neither school is 0. So the smallest it can be for the probability of E and F is 0.3. How about the largest? Well, in some ways, the largest is a little bit easier. You know you've got 1, F is 0.7. And we know that E is 0.6. Well, what if E fell right inside? This is E, is 0.6. What if it was fully inside? This would give us the most overlap. All right, so we want the most overlap and the least overlap because that's what the and is. The and is the overlap. This gives us the smallest overlap possible. This gives us the largest overlap possible. So probability of E and F would be 0.6, and that is the largest the value can be.